So I teach geography in the Geography and Environmental Science department at UW-La Crosse, and today I'm going to be talking about how we can use drones for ecological monitoring within the Driftless area. Drones can take photos and videos, but I specifically use them for mapping and ecological monitoring. So I just want to get a sense as to, has anybody used drones for mapping in this room? Yeah, so a couple of people for sure. Yeah, so so I'm going to build up from the very basics so we know what we are talking about, right? So I'm going to give you a current state of platform type sensor options what we have with drones, right? So I'm going to give you an overview, because when I was in grad school in 2008 and 2009, there was no what we call off-the-shelf commercial drones available, and suddenly by 2014, fast forward 5 years, and everybody's buying drones and flying drones and using them for mapping. So what happened in that 5 or 6 year period? We'll talk about that. How do we fly drones? We will learn that it's fun to fly them manually, but when we are doing mapping and trying to align the photos together, it's better to fly them autonomously. So how do we do that? And finally, we can collect gigabytes and terabytes of data with the images, right? And we can do some ecological monitoring, but how do we process the data? What are our options, both pricey options and free and open source options compared to what we had 5 years ago? And then finally, I'll also give you some examples of the many different kinds of applications that are out there, but there are only certain kind of applications that I am interested in. And then finally wrap it up with some future, what should we expect, right? So if you want to monitor big areas like state level, national level, we have to use images from orbital satellites, right? And one of the problems that we have with orbital satellite is we are not normally able to see what's on the ground in detail if we are looking at an area such as the entire state of Wisconsin, entire La Crosse County. So we don't make sense what's there, but if I throw in a drone imagery, now I can suddenly see this exactly. We have hundreds and thousands of pixels, and this is the UW-La Crosse campus. We can see each and every tree. So here the pixel size is 30 by 30 meter. Here the pixel size is 10 by 10 centimeter, right? So with the drone, we get a lot of detail. That's the advantage. And if you're wondering why is it red, so this is a infrared camera where the green vegetation appears red, right? So moving on, in the last 10-15 years, you can see there's this explosion of literature and research based on drones. And drones, everybody's saying they're going to save us, they're going to save the biodiversity loss, and we can monitor things better. There's an explosion of drone application and analysis in every sphere, including wildfire mapping and monitoring glaciers in Alaska or Nepal. And because of that fine level detail that we can get, and satellites can't provide that. So I just want to give you some background as to what happens. In 2007, Steve Jobs came up with the first smartphone, and that kind of changed a lot of things. Now these smartphones are kind of a small computer that can have low-cost gyroscopes, and it has GPS inbuilt. And what this led to was the development of what we call the brain of the drones, the autopilot program. And these apps that can be installed on our smartphones can communicate with the autopilot program. And prior to this, we can think about Lockheed Martin designing a big drone which will have a gyroscope and an autopilot program. It was not in the civilian domain. The launch of the smartphone enabled all of these technologies to be transferred to a public domain. And so we have these development of open source autopilot programs, right? So all of these sensors, so GPS, gyroscope, they need to communicate and take commands from a remote. So this command taking and flying should be handled by this software called your autopilot program. So with the help of the development of autopilot programs and the smartphone, we are now, what happened is you can go to a company's website and you can buy pieces of drones and assemble what we call the do-it-yourself DIY drone and download the autopilot program on your phone and start flying it. That was a little bit cumbersome, so then companies came and said, you don't need to do it, we will sell you everything assembled, and for a couple of $100s. 2010, Parrot was the company released the first what we call off-the-shelf drone, and DJI, the Chinese company in Shanghai, China, first time released this what we call the DJI Phantom quadcopter in 2013, and that was in the US the first off-the-shelf drone that anybody can buy was available, and in 2015 it really took off. So that's the history of it. And then again with the Phantom, if you go back to 2015, the way it worked was we would take a GoPro camera and try to assemble them together, and then they came up with a 10 megapixel camera, then 12 megapixel camera, and finally Phantom 4 Pro had 20 megapixel camera and HD video capability. So that's the Phantom series, which is kind of outdated now. Most of the people will be flying what you see there, kind of a gray looking, black looking drone, and Phantom was very noisy, 10, 15, 20 minutes battery time, and within a matter of a couple of years now, 1 hour battery time, cheaper drone price, and things are getting more efficient, right? Before I show you any more detail, I want to also highlight what kind of niche area is this drone monitoring, right? It's not a solution to all of our problems. If you're doing ecology, if you're doing ecological management, chances are the best data, the best quality data you'll get is when you walk on your foot, you do your transect, you do your plot, and nothing can compare probably to that quality of data. But again, you know, the problem with that is you cannot cover like a county level data collection that is just resource intensive, time intensive, even though the data quality is great. Before the drone business, we had satellite remote sensing, right? And satellite remote sensing can map the entire state, entire country, but again, the pixel size problem was there, and the only way to validate is what a satellite sees is using ground data, right? So as my PhD supervisor used to tell me, remote sensing without ground field work is non-sensing. So that was pretty, you know, important statement. So now we have drones. So this is bridging the gap between field work and what we see with satellites, something in between. Now this complements our field work because a biology faculty, he is counting you know, butterflies and insects in a 1 by 1 meter plot. And he says, Niti, can we just take a drone photo from 5 meter height so I don't have to manually count it in the field. I will just look at the photo in my lab, and that way I can speed up the process. So the drones are bridging the gap between satellite and field work, and each of these have their own pros and cons. We still can't do, even county level monitoring is not possible with drone, largely because the FAA says even if you have a drone pilot license that you need to fly, you cannot fly the drone for civilian applications out of the line of sight. You have to have line of sight with your drone. You cannot fly it above 400 feet, right? So if you're restricted with those rules, then Again, battery runs out, well, it used to run out in 20 minutes, and now it runs out for like in 90 minutes, 2 hours, which is great, but again, there is a limit to how much area you can map, right? So, if you want to buy your own drone, what's out there and how much it costs, right? What are the different kinds of drones? So the first one that you will encounter is quadcopters, and there are cheaper ones, you know. We are talking less than $1,000, 20 megapixel camera, great drones. Even cheaper ones coming in 12 megapixel camera, the mini ones, $500–600, very affordable these days. But they only carry one camera. The camera on these are not interchangeable. Let's say you want to map temperature, you just cannot take this camera out and say, okay, I'll put a thermal camera on, no, or I'll put a near-infrared camera on, no. So if you go the higher end of these quadcopters, or you can change the camera out, and what we call plug-and-play drones, and they take bigger camera payloads on and flies much more longer time. And so again, we are talking like $8,000 to $10,000 with the camera and the drone. So, and then there's something in between. So with the quadcopters, one step up is what we call the fixed wing drone, right? And this is our fixed wing drone with two of my students in Holland Sand Prairie in Holman. And again, it's going to cost more, but it flies much more faster. And if your quadcopter can map this big an area, this can in 20 minutes map 5 times bigger area. Cameras can be swapped. That's also a good point with this. The problem, however, is, as you can see, this is like an airplane. If you are in a forested landscape on the top of hill prairie and you wanna, make it land or launch, maybe you will hit the canopy. So it needs, space to launch and land. Otherwise, it will crash. Whereas what we call, let's see if it plays. And we are, let's see. Excuse me. Right here. So here's a launch of this fixed wing.
3, 2, 1, go.
So it flies really fast, maps a very big area. It has a 42 megapixel full frame camera. So even if you're flying at 400 feet, you can generate a pixel size which is 1 by 1 centimeter, right? Which is great. Whereas with our quadcopters, you have to fly low. The camera is only 20 megapixel. If you fly it at 400 feet, you're not going to get 1 centimeter. You're getting like 4, 5, 6, 7 centimeters. And yeah, so that's the trade-off. Perhaps a win-win situation is what we call the vertical takeoff and landing drone, right? So if you are in an area by 20 by 20 feet or 10 by 10 feet opening on the top of a mountain or in the vegetation like Amazon or Congo Basin, you can use this, launch vertically and then shift gears to become like a plane and fly in forward flight mode and do the mapping and come back and again switch gear from what we call forward flight mode to a hover mode and land vertically. I think I should have a video about it. So again, this is just showing you, this is our VTOL. I wish I could have bought them here, but they were a little big for my car. So right now it's hover mode, and I say, okay, reach 70 feet, and then change to forward flight mode. So only the back propeller will work in forward flight mode, and that saves a lot of battery. And then now it's in forward flight mode. It will do the mapping and come back. So those are your 3 different kind of drones: your quadcopters, your fixed wing, and your the VTOLs, right? So again, you can see how much area are they mapping, right? The same amount of time you fly, 20 minutes, it's going to map 120 acres. Your bigger quadcopter can go 200 acres, because in those 20 minutes, this guy is mapping 600 acres, flying with a 42 megapixel camera. So yeah, that a trade-off, right? I have a drone, but how do I fly it, right? Turns out, flying it's even easier when you are actually taking photos or videos. You can fly it. It's actually, I've never crashed any of my DJI drones. Yeah, my students get scared the first time I give it to fly them, but it's so easy to fly. It just takes like 5-minute tutorial. But taking photos and videos is fine, which I suck at. Drone photography and videography, I'm not good at it. But I use it for like a scientific tool, mapping, right? So when you're trying to map, you want to make the drone fly autonomously. And why is that? I'll tell you in a minute, but for flying the drone autonomously, there are apps, right? Mission planning apps. And this is what a free mission planning app looks like. This is called Pix4D, and you just download it for free, and it connects to your drone, and you define what area you want to fly, what speed you want to fly. You want to take the camera vertically down or oblique, and then there's this thing overlap that I'll talk about. And you set up these parameters. It's going to tell you that, oh, I'm going to be flying for this minutes, I'm going to map that big an area, and it's going to take me, and the flying altitude is going to be 240 feet, and then you hit go. And it's going to fly in a lawnmower pattern, click, 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 take photos of that area, and even lands autonomously. So, free app. If you want to fly the fixed wing, right, the big guy we just launched here, it comes with its own mission planning app, and that has some nuanced parameters that you have to define, like how it's going to gain the elevation, where it's going to rotate, and when it's coming back, how it's gonna land. But most of the parameters are the same. How high you're flying, how fast you're flying, how often are you taking photos, and so on and so forth. And similarly, our VTOL has, well, this can be flown from an iPad, the quadcopter, or phone even. But like this is a big tablet, right, that the company provides. Whereas the VTOL is an application that is flown from a laptop, like what we call a ground station. Again, basically, you can see this is more like flying a plane. There are a lot of modes, attitude mode, completely manual mode, semi-manual mode. You can fly it with a joystick. It flies with a PlayStation joystick actually. Basically, yeah, this is near the La Crosse airport. You can see on the map it shows you cannot fly within this boundary without FAA's permission. Okay, I'm trying to see Mississippi depositing sediments, eroding sediments, what's the budget of the sediment, right? So I want to map this area, and I define my polygon, and it tells me, okay, this is going to be a flight line. This is generating automatically. I can modify. You can fly at 120 meters, overshoot, undershoot, and then overlap. And finally it tells me with all these parameters, I'm going to map 677 acres, takes more than 2,600 photos, there are a number of 26 trips, distance between images, everything gets populated, and then you hit go, and it flies and takes photos, right? But like this cannot be done on a phone, on an iPad, it has to be a laptop. So you know now how to fly a drone, right? But what camera options, like payload, do we have? There are many yes?
Do they have sensors, like if you program it and your program has it flying smack into a tree, will it stop itself?
Yes, great question. So about the quadcopter, so the quadcopter I have here, I'm going to bring it quickly, and if you see in the front there are 2 cameras, and if you see in the back there are 2 cameras here, and if you see on the side also there are cameras here and here. So it has what we call the omnidirectional obstacle sensing. So I tried to crash it in my Subaru, it stops 4 feet away and says obstacle, obstacle. So it's pretty good for obstacle sensing, yes. And it's getting better and better. So omnidirectional, not all directional, because There is 1 or 2 degree of areas which are like a blind spot, but it's pretty good. Yeah, good question. What's talking about? So yeah, what cameras do we? There are so many cameras, right? And depending on where do you want, if you just want to make a 2D map, two-dimensional map, or you want to make a 3D map, where you want to map temperature of things, whether you want to see how green my vegetation is does it have any insect infestation, or should I be applying fertilizer in some patches where vegetation is moisture stressed and things like that. We have to use different cameras, right? So there are many different cameras available. There are some options here. Now, if you want to map gold, right, you want to identify very specific things or something that's not easy to distinguish, you might opt, like researcher opt for hyperspectral cameras. And you can see how small these are, and that has been the technological advancement we needed to integrate, make these, miniaturize these cameras so that they can go as a payload, which did not happen till early 2000s. So on the extreme end, we have hyperspectral cameras, which, you know, I only know like 4 or 5 people in the whole United States who use these hyperspectral cameras, which are very expensive. But let's say looking at these cameras, which are multispectral cameras, so with our eyes we are able to see red, green and blue wavelengths of light, right? But if you want to monitor vegetation, then we can have cameras which look in the near infrared, where the vegetation is reflecting a lot. And so we have near infrared cameras, and these are purely for scientific purpose. If you want to just construct things, measure height of things, then we can do that with our cheaper drones. So you have these cameras which are like $4,000 or $5,000, and they're becoming cheaper and cheaper and better and better. Then there are now cameras which we have red, green and blue, the visible wavelength of light, the near infrared, and also the thermal wavelength of light. So we can measure temperature, like with this camera, about $9,000. You can integrate, measure temperature. That's something I'm interested in, mapping the temperature of water in trout streams. You can monitor vegetation, healthy vegetation, not healthy vegetation, those patches, and also you have RGB, so you have like a complete picture of what's going on your area. Yeah, so you can see that that's how when I say RGB, this is what we see from our eyes, right? And for the same, this is the UW-La Crosse campus. This is what it looks in thermal infrared. So if I play them at the same time, just an animation, see, those are students walking to the classes. And both of these videos are shot by that little drone there, like 2-3 days ago. So if you go to YouTube, a lot of application. If you're into hunting, send the drone up, and the deer would have a specific infrared signature. Very easy to cheat in hunting these days, but yeah. So on the other end, there is something called light detection and ranging. So you have LiDAR sensors. So in LiDAR, you send a laser pulse, and the laser pulse strikes, and you receive the backscatter. And that allows you to measure 3D. Here are some examples of your LiDAR cameras. Again, this is slightly heavy, and we won't be able to fly it on this quadcopter. And this is a sensor that I really wish I had. We almost bought this sensor last semester. We thought we had funding, but actually that funding went to some other department, we don't know. But here is what LiDAR gives you on drone, right? When you fly a LiDAR, you can penetrate the canopy, you're hitting the ground, and you can create a complete 3D of the forest. So if you want to measure canopy height, biomass, you can look at understory vegetation height, and you have a complete picture. Now I'm going to show you in a little bit with your drone camera, like that drone camera or that $500 drone that you can buy from Best Buy right now, can also give you this. This is a 3D created from what we call photogrammetry, right? And I'm going to explain how that works, but we don't have the entire picture because when the drone camera is taking photos, right, you can get a height only for the parts which you see on the drone camera. If something is underneath the canopy that the drone cannot see when it's flying in your RGB image, then you cannot extract height for that. But nevertheless, it gives you a sense of what height is like. I'm going to explain in a little bit how this works. But this is called a point cloud derived from drone photogrammetry. This is called a point cloud derived from a LiDAR sensor. And the point cloud derived from drone photogrammetry is called poor man's LiDAR. Because the sensor is about $25,000 to the cheaper one to about $60,000. Whereas to derive this, all you need is a $500 cheaper drone from Best Buy. So poor man's LiDAR, right? How do we choose which sensor and which drone, right? So many options here. Well, it entirely depends on the application you are looking at. I'm going to show you some applications, so we'll come back to this which guide. So I have been telling you that with the drone we can do photogrammetry, we can create something 3D just with 2D photographs. How do we do that? Our eyes are already doing it, right? Our eyes have stereo vision. If we put the field of view from both of our eyes, there is this area, what we call the monochrome vision. I don't have a sense of depth here. It's the area where both of my eyes are overlapping. I have a sense of depth. This is closer, this is further, and that's the furthest I can see right now. So the sense of depth. We can do the same thing with the drone. We can take overlapping photos, right? And from the overlap, we can extract in photogrammetry something called parallax and extract height of building, height of trees, height of a lamppost. If you're into archaeology, then if you don't have a drone, how do we do photogrammetry is you want to create a 3D structure of an artifact that you just unearthed. You go around it and take a lot of overlapping photos. And if you have a lot of overlapping photos, you throw it in a photogrammetry software and it constructs a 3D for you. This process is called structure from motion, right? So to do structure from motion, you have a lot of softwares available, right? Drone Deploy, EduShaft, Pix4D, most of them you have to pay, but there are more and more softwares that are coming. You just take overlapping photos with your drone and throw the image in that free software and it creates 3D for you. Like this is a 3D, right? So now, how does drones enabling photogrammetry? So obtaining measurements of physical objects through photographs. That's what we call photogrammetry. So think about this. This is a mailbox, mail post. We're going to create a 3D of this. And we go around it and take a photo from this angle, and this angle. And if we just draw what we call lines to where the photo, and we find in our photos the same point, so that's the base of the mail post, and we draw connecting lines, it gives us a 3D point, right? And if you do that multiple times, we get like thousands of times, you'll end up having thousands of points here, and that is what we call drone derived point cloud. So it's saying having 3 or more photos, knowing camera's focal length, we can triangulate the position of a point in 3D shared in multiple photos, right? So this is what we are doing with our drone flying app. We are saying fly in a lawnmower pattern, take overlapping photos, and from overlapping photos like this red dot right here, we are identifying that, okay, this red dot in this photo is the same as this, same as this, same as this. And if we draw connecting lines, we end up having what we call a three-dimensional point cloud. So this shows a mission planning app. So area that we want to map, and you're taking these photos, these red dots represent photos. When I'm saying overlap, right? So this photo and this photo has this area of overlap, and that is what we call forward overlap. But when the drone is turning, and now we are taking photos again, and this is what we call a side overlap. We used to do this with airplanes in order to do photogrammetry. In airplanes, which is flying very high, we are taking overlapping photos. Like I'm talking now, Second World War. This is the time. That's the time when we mastered all of this aerial photogrammetry for military reconnaissance. With that, what we call aerial photogrammetry, if the overlap was 40 to 50%, it was okay. We could do a good 3D reconstruction. Now with the drones, because our cameras are so cheap and it's flying so low, what we have to do is increase the overlap between photos to 70 to 80 to 90%. So aerial cameras were very expensive, and big cameras and drone cameras are cheaper and flying more low. That's why we can still do 3D construction, but we have to increase the overlap. So I will show you this. This is what we can create with overlapping photos. This is a place called Tainter Creek in Wisconsin, and I was doing a project here trying to understand how the extreme flood is impacting stream bank, leading to bank erosion and changes in vegetation along the banks. So this is 3D, and this point cloud is only created by overlapping photos, nothing else. But again, poor man's LiDAR. It's not penetrating the canopy, right? So if anyone in this room wants to do this kind of photogrammetry for your property, where you're doing some kind of conservation, preservation, my students can come fly and create a 3D model like this.
Send them over.
Sure. Yeah, so this is a 3D point cloud. Now with this 3D point cloud, we can construct a 2D very easily. And this is a 2D, what we call orthophoto. So you took hundreds of photos and in a non-scientific term, incorrect term, stitch them together. It's not really stitching, but if you stitch them together, you get a clear picture. Pixel size is 1 centimeter, very accurate. And here, if you want to measure distance, in the software you click here, you click there, 100 feet, 108 feet, and that distance, 2D distance, is going to be very accurate, like 1 or 2 centimeter accuracy. If you want to calculate area, very accurate calculation of area. Also, you can calculate volumes. You can make the 3D point cloud, and you can say, no, I want to delete all the vegetation and see what the bare surface looks like. And that will be called digital terrain model, right? Vegetation gone. So these things are actually not that difficult to do. I'm teaching a drone mapping class this semester, and most of the students are my second year, third year students, and by the end of the semester they will know how to fly the drone, they will know all the data processing, and so on and so forth. Now this is a product which could be used for, if you do that multi-temporally every year, every 6 months. On this product, this is a 3D, every pixel has a height, right? So where the stream is eroding, where it's depositing, you can calculate that with very high accuracy. It does, stream bank vegetation reduces bank erosion, or where should we put the vegetation, at what angle that it works more accurately or precisely. We can do all of that analysis with this data sets, right? Yeah, you can produce this with a $600 drone. That's all you need. App is free, software is free. Um, Again, I'll come back to this, but now the application, right? Giving you an overview about what drones are there, what mission planning apps are there, what data processing softwares are there. Now, what can we do, right? So we can calculate the 3D volume, right? We can make point clouds, and on the point clouds, we can take them to the GIS softwares, and we can calculate the area, the complete volume by just making some digitizations like this. This is the stockpile, click, 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 and the software is going to tell you, oh, the volume and this, cut volume is this, fill volume is this, and in a matter of seconds, right? And now, a big thing, some of my students go and work for construction industry and surveying industry, and one of the big application is volume estimation in a query. 20 years ago, when there were no drones, like 20 people, 10 people, 15 people will go in this query, which are not the safest areas to be in, and make manual measurement in time 1, and then go back again and make manual measurement in time 2, and then can arrive how much volume of material has been taken out of this query. And now you can fly the drone in time 1, stitch the images together, do the image processing, produce the 3D point cloud model, go 6 months later or a week later and do the same thing again. You have 2 3D models, and you subtract the model 1 from model 2, and you get the height difference. And of course, every pixel has an area that can be calculated as change in volume. So some things, this is a query in La Crosse on the other side of the river. We were using a fixed wing drone for my drone class. I haven't talked about this, what we call the ground control. If you want to align the 2 models, you want to compare, right? So one thing you have to make sure is those 2 models are aligning in space properly. And in order for those models to align, you need to have ground control. These control areas are areas which are not changing in X, Y, and Z over time. And yeah, that takes a little bit of time to install. But if you have installed, we take like a 6-foot rebar, put it in the ground, and the cross right here is right on top of that rebar. And we do that probably all around the query, 5 or 10 places, and then we are ready to do this multi-temporal study. I also like working on glaciers and how glaciers are changing, right? So I have taken about 10, 12 students to me in Nepal, and we found out a glacier, and that's called the Annapurna 3 glacier. It's one of my students here, he graduated. This is from 2019, and that's me flying the quadcopter. So basically, this is how the glacier looks like from satellite. A lot less detail, right? We don't, pixel size is 3 meters, but now the drone imagery, and suddenly you can see this ice cliff. Pixel size is 3 centimeters here. And this is how it looked like in November 2019. With the glaciers, they're melting so fast, and the satellite has so much uncertainty. The drone has very precise measurement, and the volumetric change you can calculate by comparing the 3D model in time 1 and time 2 very accurately. So we went in May 2019, and this was in November 2019. And then for this common area, we were able to map slightly bigger area in 2019 November because there was battery charging facility. So up here is like 15,000 feet. I couldn't climb any further, so I sent the drone from here. Basically, if you show you the photo here, so we were standing right there somewhere, and the drone went there. And I could not see where it is, but on my tablet I could see its mapping. And my drone is supposed to fly for 40 minutes, but at 14,000 feet it's flying for 20 minutes and the battery is draining, right? So lots of challenges. Temperature is in single digit Fahrenheit, battery draining faster, but ground control is important if you want to compare, right? I'm not going to go into a lot of detail here, but that is an animation showing the change between those 6 months. So you can do this kind of change and calculate how much water is coming out of this glacier, and it turns out that these ice cliffs that looks like this, right? They occupy maybe 5 to 10% of the glacier, but they generate 50% of the melt volume. That was very surprising, and yeah, this changed between 2 dates in 6 months. There are some methodological contribution here that I'm not going to talk about, called digital surface model differencing versus point cloud differencing. When you have 2 point cloud and you difference that, that is actually giving you a better result of how much melt is coming out versus if you difference the digital surface model. Locally here, I have been working on a project with the folks in biology department and US Fish and Wildlife Service and USGS, mapping invasive aquatic species, this purple loosestrife, using drones because it gives you a lot of detail, right? So this has invaded all the counties in Wisconsin, purple loosestrife, and we don't have a good estimate of how much an area it is actually invaded and how much more area it will invade. So we wanted to see if we can map these things out very accurately using the drone imagery, again stitching the images together into an orthomosaic and seeing how much area is there. So Bryce Prairie Conservation Association, which is a conservation organization, they provided a lot of student support, logistical support, board support to data collection. Again, we were going in a boat like this in the middle, and that Lake Neshannock, if you're familiar with that area, flying the drone, like holding like this and launching it from the hand, and then once it's mapping done, somebody will grab it, and you know, we did that from the boat. And so again, field work, right, and biocontrol to reduce the impact of purple loosestrife. You can only cover so much ground, right? And they released Beetle, the Bryce Prairie Conservation Association, and we did a mapping prior to the beetle release to see how much damage can the beetle do as a biocontrol. And we went back again the next year to map it, but unfortunately the flood level was so high, everything was underwater, and we could not do the multi-temporal study. But nevertheless, there are 2 areas that we looked at. One was the Bryce Prairie by the Mississippi Wildlife Refuge, and Lake Neshannock using a quadcopter. So what we did was, you again acquire imagery, and that's our purple loosestrife, stitch the images together, you have a mosaic, and you can go in a GIS and map the patches out. And this is how it looks on the ground. It looks very nice, but actually ecologically it's doing a lot of damage. So you can do manual mapping and arrive at a very accurate number of how much an area they have occupied, and you can then monitor the change over time. But manually digitizing this takes time, right? Wouldn't it be smart to train a computer algorithm to identify it automatically? And that is something we are working more recently. So if you go into artificial intelligence and machine learning, there is a specific set of technique called deep learning. And we are trying to train a deep neural network model to train it to how loosestrife looks like. And if we train it properly, then it should be able to automatically identify in a much larger area and much bigger scale. But training it takes a lot of time and lots of samples. So this is a work in progress. Again, I have more things to talk about, so I'm going to skip this, but this has potential, and we are working on this part. Now, Other application is mapping trout streams. Can we map trout streams, and maybe there are some trout streams which are not designated as trout streams. Can we identify that at watershed scale, not one watershed, but like 5 watersheds, 10 watersheds, 20 watersheds. So if you want to do at that level of analysis, you have to do satellite image, right? And so Iowa DNR, they did data collection, and they found, yeah, there is trout. There are streams which are, you guys all know more about this than I do. A lot of streams that are designated as non-cold water streams are actually cold water streams. So we wanted to figure out what's the level of uncertainty. So we selected Coon Creek watershed in northern Iowa, which is in the Driftless area. And assumption here is if we have a what we call high resolution satellite imagery, pixel size is like 30 centimeter, 40 centimeter, and it's peak winter, like talking February, January, it has been very cold for the last 2 weeks, and now the satellite acquired image. And if we see an open channel like this, that means there is a spring here, groundwater is being discharged, and that's why there's the only reason that this stream will be open and not frozen at that temperature is this is a cold water stream. So our assumption was that if it's a peak winter imagery and we see open water, then that means it's a trout stream, it's a cold water stream. With this assumption, we checked it in multiple locations. It was true, and this image that we see has a spatial extent of entire Wisconsin in one single image at 30 centimeter. So remember, with our drone imagery, we can probably map just this city right here. That's the limit, and we'll run out of batteries. But with one satellite single snapshot, we are mapping this whole area, right? Going like 180 miles from north to south. And if we can figure out a methodology to find trout streams in this imagery, that's going to be path-breaking research, because then we can not only map streams at a local scale, but we can go watershed scale or much bigger area and say, okay, in this bigger area, this is the number of streams or length of cold water streams we have. So we looked at this watershed, and in this watershed we had extensive temperature logger data, we had fish sampling done at these locations, and that we were using to ground truth. So we looked at winter imagery, and you can see there are areas which are very clear and very wide, and there are areas which are kind of, the stream is very narrow, it's frozen in certain sections, and then it's open water in another section. So it varies a lot. And then we did the visual interpretation, and we found that within the single watershed, there were like 35 kilometers of stream plus 21, like 70 kilometers of streams that were actually cold water, and that in the DNR designation it was not cold water. So we recommended that this be assigned to cold water designation. But that doesn't mean the satellite is telling the truth, right? How do we understand that? We have to use the drone imagery. So we went, again, that was just for Canoe Creek watershed, but this is showing you 6 different watershed. And if we enlarge the area, we find even more longer lengths of cold water streams that were misclassified. But you can see there are 2 different images in here. This is open water. This is from satellite, 30 centimeter pixel size. We went to this location in summer, and on the ground took an oblique photo, and this is how the stream looks like. And on the ground, we sampled trout here at this point. This was 2 meters wide. We found out that with the drone, we can see this again, we sampled trout here, 2 meters wide, which is like this. Even with 30 or 50 centimeter satellite imagery, we cannot map this out. So satellite imagery cannot identify areas that are less than like 4 or 5 meters wide, and which are still very high quality trout stream. And moreover, there are bigger issues with satellite imagery where there is overhanging canopy, right? At this site number 4, we went in the summer, and this is completely covered by overstory vegetation, as the field photo suggests. And our high resolution imagery says this is not a trout stream. I mean, so hard to interpret where the stream is, right? Even if it's 40-50 centimeter winter imagery. So we are still missing a lot of quality trout streams, which we can see in drone imagery, but not in high resolution winter imagery. So I hope that makes sense. Satellite imagery, even in the winter, 30 centimeter, it has limitations. I think how much time do I have?
You can take as much time as you want,
Okay.
not on a specific.
I'm gonna wrap this up so I can take some questions. So, another project that I did a couple of years ago is, can we map vegetation phenology, right? So we know what phenology is: vegetation greening up in the spring and then dying down in the fall. And turns out there is North American Phenology Network. This is a network of oblique camera placed strategically at 26 different locations throughout the lower 48 states, and this taking photo every hour. And in that photo we can analyze that photo and see how, in what time of the year the vegetation is actually shedding leaves or changing, fall colors are peak, and when the vegetation is greening up, right? And turns out, because of climate change, our summers are becoming longer, and that means the spring onset is early and the fall onset is late. That's the length of growing season is changing. But again, the satellite has only that pixel size problem. With the drone, I argue that we can look at that at species level. Maybe this is a different tree species. When does this tree starts growing up? And this is a different shrub species. When does this start growing up? We can do that if we take photos every week and stitch them together into a mosaic, right? So that's what we did with the Holland sand prairie. We went into the ground, we identified different prairie vegetation species with the help of Jim Rogala in USGS, who's retired now. And then we went and cropped out the canopy of a known vegetation, like this, June 19th, right? And we flew every week, right? So we can take these pixel values and calculate something called green chromatic coordinate. So higher values tells you that this is more green. And for that polygon, what was the green chromatic coordinate value in the beginning of spring, and then how it increased as the spring sets in. And then with this green chromatic coordinate value, we can do some curve fitting, and we can do it for every other species on the map and see when it's picking up. And again, this was some camera calibration issue that I figured out, and I couldn't find very distinctive results because of some technical issues with the camera that I used. So that I would like to revisit that project in the future sometime. But I think that's it from my side. I hope I was able to give you a good sense of, at least vegetation monitoring. I would like to tell you this in conclusion, that if you want to measure the volume of things, how big or how high something is, the geometry of things, like the glacier change, how much is the volume is taken out of the query, that is what we call volumetric change. The geometry of feature and changes in geometry, that is not challenging to do. I shouldn't say not challenging, that is doable with our RGB cameras, normal cameras. But if you want to monitor the radiometry, how the greenness in vegetation is changing over time, that's the radiometry component. You're not looking at structure, you're looking at the greening signal with cheaper cameras like the $500, $600 cameras. That's kind of hard to calibrate cameras, and when you're comparing something radiometrically across time, there are so many variables that can mess up your, will introduce bias and mess up your analysis. Over the last 10 years that I have been doing this, 9 years, drones are becoming even more cheaper, battery life is becoming longer, more and more software options are opening up, softwares are becoming cheaper, drone flying apps are, like there are 10 options now, free of cost, download and fly. When I started 7-8 years ago, there was like 1 or 2 options. Similarly for data processing, there are lots of free open source software that you can use, and drones are becoming cheaper, the cameras are becoming cheaper. Now you can buy a drone in $5,000 to $6,000, which can fly for 3 to 4 hours. I cannot use them because I'm flying them in populated areas and I have to stick to FAA regulations. I try not to fly it out of line of sight, but there are moments that I have lost a track of the drone. But you can go to YouTube and you can see videos. There are some crazy people sending the drone like 5 miles away and saying, hey, I made a record, and posting that on YouTube. And for the law enforcement to, catch them. And so don't do that. Follow the rules. Yeah, like I'm looking for local research opportunities that I can collaborate with people. Yeah, federal, like anytime I want to fly on the Mississippi River, there are paperwork that takes time, but US Fish and Wildlife folks have been very supportive, and there are lots of people from these organizations that have supported my students financially, provided logistical support, so I'm really, really thankful for them. There are like at least 40-50 students that I haven't put their name up here, but yeah, I acknowledge them. And